and FAD, the second group. Then go here, coenzyme Q. Then go here, cytochroma C. Sometimes right here they have another one, which is cytochroma B, and then goes here, cytochroma A, A3, and the final goes to oxygen. So the electron transfer like this. This is I mentioned a couple of times, so we're going to go detail. What's the story behind it? So it's a standard electron transfer chain. We're using this as an example. That's an example. So the second question. Where are the locations of electron transport chain? And you should be very clear. Where are the locations? For bacteria, it is at cytoplasm. You can easily understand it. It is at cell membrane system. How about for fungi? Yeast, molds. This is because it's a eukaryotes. So same as you learned in your other classes. The location is mitochondria. Okay, this is the first thing you need to know. Second, this is number 3 here. Why is the order like that? Why NADH is always on the top, followed by FAD, followed by cytochroma coenzyme Q, then cytochroma B, B, C, AA3, and finally is oxygen. So we are talking about why this order is like that. We want to talk about several things. Number 1, the electron is always transferred from a donor to an acceptor. Or we could draw another thing. Is acceptor becomes donor. Okay? So this is a one. Someone will accept, someone will be donated. Now, how do you know it is a good electron acceptor? How do you know it is a good electron donor? What we are doing called two-half reaction. Now, what means a two-half reaction? Obviously, you have an acceptor and you have a donation capability. So, we separate them into accepting capability and donating capability. And then how we determine that, then the question is. Therefore, we did something using voltage, using volts to evaluate reduction and oxidation capability. Okay, so we use volts, voltage to evaluate. If you see the E prime value is negative, which means it's more pretend to be pretending to be a good electron donor. If you see this E prime is positive, That means it's more pretending to be an electron acceptor. Okay, so what that means? Gave you some example. You can look at the table. NAD, FAD, just give me some example, and oxygen. This is the voltage value. You see the NAD is about minus 0.4. FAD is about minus 0.2. How about the oxygen? Is plus 0.8. Therefore, it tells you NAD, FAD, and oxygen, it's going to be a good electron donor. And the oxygen is very positive. It will be a good electron acceptor. So, based on the 2-half reaction, we see the electron value. The electron is transferring from this way. Because at the top, it's more potential to be an electron donor because its voltage value is more negative, and at the bottom is very or more positive. Okay, so this is the first thing I want to mention. Second, which is number 4 right here. And we know that NAD reduced to NADH2 will create 3 ATPs. And FAD reduced to FADH will generate 2 ATPs. And by the way, this is an older calculation. The new one, when we talk about oxygen phosphate ratio, this becomes 2.5 ATPs, and the bottom one becomes 1.5 ATPs. Now, the question is, why NAD reduced to NADH2 is 3 ATPs? Why FAD is only 2 ATPs? Because the distance between NADH and oxygen is the distance between minus 0.4 to plus 0.8. And the FAD and the oxygen, I can write right here, the distance is minus 0.2 to plus 0.8. So you can add them together. This is 1.0. This is, of course, approximately. This is approximately 1.2. Because the voltage difference between NADH to oxygen compared to the difference between FAD to oxygen, the former one is larger than the later one. That's why NAD generates more ATP compared to the FAD. Okay, so here comes another thing, which is the more difference between electron donor and acceptor, the more energy generate, which means ATP is generated. Okay, so this is something we really want to mention before we move on to. Now we go back to see the slides. First of all, they come up with 2-half reaction. And you see the table here. What means 2-half? One is electron donating, another one is accepting. Okay, so we use acceptor, add E donor to see the difference. You can see NAD minus 0.32, close to 0.4. But the older book is minus 0.4. FAD minus 0.18, close to minus 0.2. Oxygen is 0.8. Okay, so bottom of these start from flow rate. to cytochrome C, ubiquinol, all these, it's very positive. So they are potential to be electron acceptor, and when on the top you see this negative value, which means they are potential to be electron donor. So that's why we have a 2-half reaction. And this tells you the conclusion coming from the last slide. The more negative electron value, which means better electron donor, and the more positive is the better electron acceptor. And this tells you, I just wrote there, the greater the difference between voltage value between donor and acceptor, the more energy will be generated. This is using delta G here, which means the free energy coming out. Okay, so you can see from here, if the distance from NAD to the oxygen, and compared to FAD from the oxygen, the former one is more large difference value compared to the later one. That's why more energy is generated. And this tells you where it is, where are the locations, and there's so many chemicals. And this tells you about the locations. And this gives you some of the example. Okay, NAD, that's we're using a lot. Nicotinic adenine dinucleotides. We already mentioned in the exam 1, exam 2. NADP, nicotinic adenine dinucleotide phosphates. This one we probably not going to mention in this class. This is using for carbon cycle. Okay, the carbon dioxide fixing cycle. We're not going to talk about this in this class. Fulvene adenine dinucleotides, FAD. And here, which tells you something about their formula. Okay, and now we want to mention something else. Used to create a protein motive force that can be driving ATP synthesis. That's for NAD. Carrying 2 electrons and 1 proton. Proton, which means hydrogen bonds. Fulvene adenine dinucleotides is also, we say, used to create a protein motive force. Can drive an ATP synthesis. Now, what this means? This is something we want to explain to you. Okay? I'm going to take this one out. To draw here and then explain to you. The story is right here. I still keep this. Okay. The concept, when we talk about PMF, proton motive force. This is actually, we are talking about potential energy become kinetic energy in bacteria. To explain this terminology, we have one terminology to describe it, called chemosmotic theory. This theory created by a British scientist, Peter Mitchell, in around 1940s, and this is 1968 Nobel Prize. So it's a big contribution to the scientific area. This guy probably 1912 to 1992, around like 80 years old, a pretty long life to the old, in the old times. Okay, so what is this one talks about? We know the bacteria membrane system is like this. Okay? So we were moving this guy right here. So we have NAD. We have FFN and FFES and Fe. We have cytochrome Q. That's the difference. We have oxygen. Okay? Just like this, the electron is transferred. The electron transfer. Once once the electron transfer during the electron transport chain, they will do something which is repel a very simple chemical, which is called H+, accumulated outside the cell membrane. And we have another name for the hydrogen ions, we call it proton. Now, how they do this? We know there is an enzyme called dehydrogenase. Look at the dehydrogenase. ASC means an enzyme. Dehydro, which means you take out of the hydrogen. And hydrogen at this moment we call the proton, have another name. So they accumulate. Once they accumulate more, this becomes the potential energy. Now, in the human life or bacterial life, they always happens if something is accumulated more outside of the cell membrane, there is a possibility they could become back. They're always, you have so much money, you try to buy something. It's all like that. You have so many protons outside of cell membrane, they can't try to screw it back. Okay, because there's a lot of the channel for it. Once these guys comes back, what's going to happen? They will be activate an ATPase. Okay, ATPase is a complicated enzyme. We call it a hollow enzyme. We'll mention real quick. Okay, it has a coenzyme, cofactor with Apple enzyme. So it has alpha, omega subunits, beta, and F1, F0 subunits. It's a good complicated combination. And then they do the rotation when they activate. Now, what did the ATPase they do? Of course, it's let's ADP with phosphates then become ATP. Okay, so they generate ATP. Once they generate ATP, what the bacteria going to do? Bacteria will do twisting. Will do a rotation or rotating. Then what is the major structure for bacteria moving? We learned about in the lab. It's called a flagella. So that is the whole story. Okay? Once the electron transport chain transfer electron, they are coupled with repel proton outside of the cell membrane, then become a potential energy. And this relies on dehydrogenase. And once you have a more proton accumulated outside of the cell membrane, they always try to back. And once they try to back, they activate ATPase. And ATPase, the hollow enzyme, it will trigger ADP, combined with phosphate becomes ATP. And once that happens, the bacteria start to twist it, start to rotation, rely on the flagella, so coupled with flagella rotation. And this is the story called the chemosmotic, and why bacteria can generate energy during the electron transport chain. Now be careful about that. When he did the research at the beginning, he found this mechanism behind it. Does not mean every chemical here will be transferring electron and repel proton. Let's say this guy, coenzyme Q. This guy only transfer 2 electrons to downside of electron transport chain. Coenzyme Q not repel proton out of the cell membrane. Therefore, for coenzyme Q right here, there is more research needs to be done, and there is still unknown. We call it Q cycle. Okay, just want to let you know, it's still something is unknown right there. Does not mean everything they do the same, but most of them let's say we have NAD, we have FAD. They do carry 2 electrons and 1 proton, so they are transferring 2 electrons, and they will be repel 1 proton outside to the cell membrane. Okay? This picture here, which is well explained, the typical fate of the electron carrier, which means NAD and FAD, they are generate proton motive force and can driven ATP synthesis. And that is the story. Okay? Now, by the way, this whole thing, we have a terminology called it. What we call it? Oxidative phosphorylation. Is that right? So what is this terminology? How to explain oxidative phosphorylation? We get ATP, we get energy currency coupled with electron transport chain based on the theory of chemosmotic. Now, what is substrate level phosphorylation? The phosphate simply transferred from ADP to ATP, rely on the chemical, has a high phosphate transfer power, like phosphophenols, like glyceroldehyde 3-phosphates. Now, when we talk about glucose 6-phosphates or fructose 6-phosphates, those, they still have energy, phosphate transfer energy, power, but they're very low. Okay, not as much as ATP itself. Okay, so this is ATP synthesis, chemosmosis. Okay, so these are the pictures you have to well explain. Okay, and you have to be well combined to understanding all these things. Okay, once we finish here, we are going to move on to right here, metabolic apostolate. Okay, when we talk about metabolic apostolate, we only going to mention 3 things. And this slide will explain. It could be linear, which means A to B to C. It could be a branch. Okay, the branch looks like this. And it could be a cycle, a turnaround, a circle. Okay. 3 different types of the metabolic apostolate will explain 3 different biochemical reaction. This is fermentation. The branch reaction, glycolysis. The last one, citric acid cycle. We will talk very detailed on Thursday about all those 3 and related to ATP calculation, and we will review again for oxidative versus substrate level phosphorylation. Okay, so this slide is easy. You understand about that. Fermentation is the first one. Second one is a branch reaction, glycolysis. The last one, a circle, is citric acid cycle. Now we're going to spend some time to talk about the enzyme. Okay, what's the story for the enzyme? So we're going to take this one off. Take this off, then we talk about the enzyme. Okay, first of all, why do we need an enzyme? This is very simple. We want to these metabolic pathways, this reaction, happen as quickly as possible. Typically for bacteria, their lifetime is very short. We want to have these things happen as soon as possible. So that's why they need an enzyme. Okay. So, they would love to let biochemical reaction happens as soon as possible. Now, what's the basic structure? What's the basic function of the enzyme? Very simple. You have a substrate. You have an enzyme. Then you will generate a product. Now for bacteria, basically you generate acid, alkaline, gas, which is come up with a color change on the media. That's why we can test in bacteria. Okay? So that's a very easy formula. Now, why enzyme will let a biochemistry reaction happen as soon as possible? Because they'll decrease the required energy for reaction. So let's say the normal, you need so much energy. And if I put enzyme, you only need much less energy to let it happen. Okay? These are the gaps between that. This is the function of the enzyme. Number 4. How do you know it is an enzyme? Anything you have ASE is an enzyme. It's very simple. Catalase, ASE, urease, ASE, hydrogenase have ASE. Okay, so the letter you have ASE, it's an enzyme. Okay? And the enzyme kind of is that, I will say, usually specific to substrate. Okay? Now we want to mention something else. Everybody knows enzyme is a protein. But does not necessarily mean it's only a protein. There is a different structure. Okay? So we'll talk about this in enzyme. There is a protein parts and non-protein parts. The protein parts, we call it apple enzyme. The non-protein parts, it depends. If it's closely attached